So welcome back for the fourth lecture of this week. So we have been talking about topic models, and in the last lecture we had covered what is generative model of LDA and how do you use Gibbs sampling to estimate the parameters of LDA by using the observations as your various documents and what are the words that are occurring in the documents. So in this lecture and the next, we'll be talking about different variants of LDA and how do you use that for different applications. So we may not cover many of these topics in detail, but once you get the idea of what these variants are given an application, you can go and look more into these topics. So this lecture I will be starting with some sort of class exercise on Gibbs sampling, that how do you estimate parameters from a given Gibbs sample, and then we will go forward for the variants of LDA. So let's take this example problem. So what you are given here, so you're saying that there is a corpus that has 5 documents. So 1, 2, 3, 4, 5 at document ID is here, and 5 words: river, stream, bank, money and loan. And there are only 2 topics that you want to estimate. Now this is when you are doing Gibbs sampling. At certain point of time you are given what are the different assignments of topics to different words in the document. So what do you see here? Document 1 has 4 words bank, 1, 2, 3, 4, 5, 6 times money and 6 times loan. And at that point of time, all these 16 words have been assigned to topic 1. So black is topic T1. Document 2 has most of the words assigned to topic T1 and 1 word to topic T2. And so on, you are given the topic assignment at a given point of time. Okay. So you can see that the first row indicates that the document 1 contains 4 words, 4 instances of the word bank, 6 of word money and 6 of word loan, and black and white circles are topic T1 and T2. Now your task is that you want to use this structure to estimate different parameters of your model. So remember what were the 2 main parameters? One was your theta, another was your beta. Beta is what is the probability of a word given a topic, and theta is what is the probability of a topic given this document. So in this example, we will try to estimate 2 different beta values. That is, what is beta money 2, probability of money in topic 2, and beta bank 1, probability of bank in topic T1. And you are given that eta and alpha are 0.1. Now, if you remember the formula, how do you compute beta money? For that, you will need to use your matrices. Okay, remember you consider 2 matrices, C WT and C DT. C WT, this word assigned to what topic, DT, this document what are topics that are assigned. For this problem, for beta money, intuitively what is that? What is the probability of the word money for the topic T2? Okay, so you will need only this matrix, this word assigned to what topic. In terms of this matrix, how do you write this particular parameter? You say C WT. So if you have to write IJ, ith word, jth topic. So let us say this is my I and this is my j. So this is IJ plus you have used the hyperparameter eta, divide by, now you see all the different words that are assigned to this topic, summation over k, C WT, WJ, sorry, this should be kj for all k plus w times eta. So this summation k, this is for all w, and that's why you have w eta here. That's how you estimate this parameter beta money 2. So let us see how do we estimate this parameter from this matrix. So one thing is that you will have to first construct this matrix. So let us see what does this matrix look like. WT will have 5 words, right? River, stream, bank, money and loan. And you have to find out how many times this word has been assigned to topic T1 and T2 and not including this instance. Okay, fine. So that we cannot do at this time, so we will take all the instances. So let us see. River. river is not assigned to only topic T1, black. So river is not assigned to topic T1 at all, only to topic T2. So I have 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9. River is assigned to topic T2 9 times. Okay. Stream again 3, 3, 6 and 6, 12. 0, 12. Bank 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 times topic T1. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, topic T2. Money only topic T1, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, 13, and 4, 17. And loan 1, 2, 3, 6, 10, 13. That is your matrix CWT. Now, let us see how do we compute beta money for 2. So, you have to compute CWT Ij. I is money, yes, and J is T2. Okay. So, this is 0. It is not assigned to topic T2 any number of times. So, I write 0 plus eta is 0.1. Now, divide by summation over k all the words. All the words that have been assigned to topic 2 here. So, I will just add this column 9 plus 12 plus 16. So, that will give me 37 plus W number of words is 5 times eta, this becomes 0.5. So, this comes out to be 0.1 divided by 37.5. Similarly, can I compute beta bank 1? For that I will find out how many times bank has been assigned to topic T1 11 plus eta 0.1 divide by summation over k C kj wt. So, that will be how many words that have been assigned to topic T1. So, it will be 11 plus 17, 28 plus 13, 41. So, 41 plus 0.5. So, this comes out to 11.1 divided by 41.5. So, like that you can compute all your different betas at this given time point. Similarly, you can compute your thetas. So, this you can take as an exercise, find out what is theta for document 1 or 2 for different topics. Okay, this is something that you can do. Now, one more thing that might be interesting. Suppose I ask you a question that find out in this iteration what is the topic that will be assigned, or what will be the multinomial distribution from which you will sample a topic for a given word, like the first bank in this document. Okay. First, there are 4 instances of bank. For the first instance of bank, you have to assign a new topic. That is what you do in iterations. So, for that you will have to again compute different betas and thetas, but what you have to keep in mind, you have to exclude the current instance. So, when you are computing this, you will remove the current instance. So, suppose this is 11, so we will remove the 1 from here, and so on you will compute these values. And from by removing the current instance, you will compute the betas and thetas and use your formula for find out what is the probability for topic T1, probability T2. From this distribution, you will sample a topic. This is something that you have to keep in mind. So, this was a simple example for how do you use Gibbs sampling to estimate your parameters. Now, we talked about certain applications of LDA in the last lecture. So, we saw that we can use it for computing similarity between words, to compute similarity between documents. That are some of the very promising applications. But what are some other different tasks where you can use these topic models for? Firstly, let us see the simplest task, that is, can we model the documents using the topics? That is the straightforward thing that you can do using this LDA. So, here is something, the collection, that was also one of the motivation with which we started these topic models. So, you are taking collection of science papers from 1990 to 2000. So, there are 17,000 documents and 11 million words there, and there are 20k unique terms, 20,000 different terms after removing the stop words and rare words. Now, on this collection, suppose you run your LDA model. So, for running the LDA model, you need to tell what is the number of topics. Suppose you say you have 100 topics. So, once you have run your model using your 100 topic models and you can use either Gibbs sampling or variational inference. So these are two different possibilities for estimating your parameters. Now, once you have done that, try to see what do your documents look like, what are the topic distributions there. So when we do that, so remember this was the article that we were looking at, seeking life's bare necessities, and this was a genetic in the parenthesis. So we found 3-4 topics there, right? Computational, some data analysis, some genetics, evolutionary biology, and so on. Now, suppose we run this topic model over this whole corpus, we find out what happens to this document. So this document gets a probability assignment like that. So there are 100 topics, and some topics get high probability. So there are few topics that are getting high probability. And then we go back and look at these 4 topics. What are the most common words in these 4 topics? So we see something that we were looking for. So we saw first topic contains words like human, genome, DNA, genetic. So it's about genetics. Then the second topic about evolutionary biology, third about different diseases in bacteria, and fourth about data analysis. So these are the 4 topics that come on top. And this looks very interesting that you do not give any information to this model that this document contains these topics or this document contains these topics. Still, by learning from a large corpus, it was able to learn different topics and the topic assignment for a given document. So this is very interesting aspect of LDA. So now, apart from modeling the simple topics that are there in the document, what else can be modeled using these topic models? So we will see how do we model different other assumptions in the data. So till now what we are saying, so we have a static data. So we have a static data over whatever time it spans. So there are a fixed set of topics, and the topics are also kind of independent of each other. You do not say, okay, if in document topic T1 occurs, then T2 should also occur. We do not say that. But can we also model these assumptions? So for that we have different models like correlated topic models, dynamic topic models, and measuring scholarly impact. So we will see how do we go from LDA to any of these variants. So let us see the correlated topic models. So right now what we are doing, we are having a distribution that helps me sample the probability distribution of topics for a given document. So this is what? This is some simplex where there are positive vectors denoting the probability that add up to 1. However, in this distribution, the components of the probability distribution are quite independent of each other. So that means they do not model various dependence between the topics. So suppose I want to say that there is an article about fossil fuels, and if I know the topic fossil fuels occurs in the article, probably the topic about geology may also occur rather than genetics. Okay, this is something that I might know, that these 2 topics are quite correlated and these 2 topics are not correlated. So can I use this intuition to better learn my topics and distributions within the documents, that certain topics are correlated, they will occur together, certain topics are not correlated, they will probably not occur together. So this cannot be modeled by using the digital distribution, so we use different distribution to model the topics in a document, and that's where we use the multivariate normal distribution. So something like this. So you are having k topics, so you will have a multivariate normal distribution where you are having you are sampling this k dimensional distribution, but now from this normal distribution with a mean and covariance. So mean will be what is the prior information that you have about different topics, what will be the mean of the different topics, and sigma will be how are these different topics correlated with each other. That's what you will try to give as in your model. So how does your model change? So everything remains the same, except that instead of sampling from a digital distribution, you are now starting to sample from a multivariate logistic normal distribution with a mu and sigma. So your eta d's are sampled from this distribution, and so that's where the topics can exhibit various correlations, that these 2 topics are correlated with each other while these 2 are not correlated. So once you have done that, finally what you will get, you will again get your k topics, right, like the 100 topics you are doing in the case of science, plus you will also know which 2 topics or which pair of topics are correlated with each other. And this can be very nicely used to give a map that these topics are make a single cluster or single group, they are correlated to each other. These topics are again another group that are correlated with each other. So, for example, if it is and how do you know that this works better than LDA? So, one good method of evaluation is that you try to find out what is the log likelihood that it is providing to a held out data. Held out data is some data that you did not use for training of your topic model. Okay, so you do not give it as an input for Gibbs sampling and or variation inference. So, once you have learned the topics, try to see what probability it gives to a held out data, some separate data, again from a same domain. So, whatever topic model gives you a better log likelihood, that is probably better, that is a better model. This is similar to what we did in the case of language modeling. We found out what is the perplexity that it assigns to a held out data. Similarly here, what is the log likelihood that it assigns to a different held out data. So, we see if the correlated topic model gives a better likelihood than the LDA, simple LDA, and that is what you see here. So, this is on a held out likelihood on a number of topics. So, interestingly, if the number of topics is small, say 30 to 40, both models give the same log likelihood. But as you increase the number of topics, the LDA model, the likelihood given by LDA model starts decreasing, but this does not happen with CTM model. So, that means if you want to have more topics, then CTM is a better choice than LDA. CTM can model richer assumption in the data than LDA if you have more number of topics. So, that you can see here also, the likelihood difference between CTM and LDA, it keeps on increasing as you increase number of topics. So, this is how the map will look like. So, you will see here, this topic talks about United States, women, universities, students in education, and it is about research funding support, scientists and research people. So, these are correlated topics, but they are not so correlated with topics like here, stars, astronomers, universe, galaxy and galaxy. So, which again make different sort of clusters for topics, and this is modeled simply by using the covariance matrix. These topics are connected together. Now, so this was one assumption that we can model. Now, suppose let us take another assumption, that is which topics are correlated to each other and which topic, how do topics change over time. So, right now what we are assuming, so you have a static corpus and in which there are the same topics over time, okay, same set of topics over time, and by same topic I mean the distribution of words in the topic are also same over time. But this is not true in general. Suppose you have a collection that spans on multiple decades or even centuries, say 200 years of data. So, what you will see, within the same topic, the number of the type of words that you are seeing over the time are changing. Initially, you will see some different sort of words, and later on you will see some different sort of words. Topic might be the same, but then the kind of words will keep on changing. Also, the probabilities of words will keep on changing. Now, this you cannot model by the simple LDA model. So how do you actually specify this? And that is where a dynamic topic model is used. Okay. So, what is the problem with LDA? So, it assumes that the order of document does not matter, and this is not appropriate for the corpora that are spanning for hundreds of years. So we might want to track how the language within the topics are changing over time, and for that we use dynamic topic models. So, it is very interesting. This is just a direct extension of LDA, but now you model that, okay, how the topics are changing over time. So, how do you do that? So, when you have a large collection, you will divide it into multiple different time points. So, you say this is your corpus 1, corpus 2, corpus 3, corpus 4 and so on over time. So, you are starting from 1 up to the last corpus. Now, when you define your topic distributions, you say that, let us say the initial corpus had distribution beta k1, okay, beta k for time step 1. So, what you will say, as you go from time step 1 to time step 2, the next beta will not be the same as the beta 2 will not be the same as beta 1, but will be again a distribution starting from with the mean of beta k1 with some variance. So, that is, you are allowing to change the probabilities of words within the topic model, and that you can do over time. So, that is, the previous topics influence the next topics, but the next topics can also change with certain variance, and this is how the model looks like. So, you are having timestamps from 1 to t, So this is same as if you are having T capital T different corpus, and you are running topic model for each corpus. But now you are not doing it independently because your betas are connected. So you are saying beta k1 is an input to beta k2. So this is like a normal distribution. Beta k2 is like a normal distribution with a mean of beta k1, but with some variance. So you are biased to take same words with same probability, but with certain variance. So that will allow changing the probability distribution of words and also having new words in the topic model. Okay, so that is the only change that happens. So you are having different betas over time, but they are connected, starting from the first time up to last time. So what you are seeing, the previous time point topic models will influence the topic model at the next time point. Now, once you have this dynamic topic model, how it can help? So suppose you are modeling how in science a particular topic is changing over time. So let us say this is modeling of science is starting from 1881 to 2000, and the topic is atomic physics. So what you see, the kind of words that are there in the topic keeps on changing over time. So here you have words like force, energy, motion, differ, light, measure, magnet, direct, matter, and result. Okay, but as you go over time, the words here are energy, electron, magnet, field, atom, system, to quantum physics. So you see the word quantum comes up and the word electron comes up, that are not there in the initial time point. So this you can see also over the time, and this is a nice plot that shows how these three words vary over the decades in this topic. So see, initially you start with matter having a very high probability, but then it starts decreasing over the decades. The word electrons comes up, okay, at certain time point. This is around 1900 with this cathode ray experiment, and this is like stable, electron is stable over time. But then a new topic on quantum also comes up, okay, and that is having a very high probability. So this gives you a nice visualization that within a given topic, how the words are evolving over time, how this topic is evolving over time. Similarly, if you see the topic of neuroscience, you can similarly observe that initially the word nerve was having a very high probability, but over the time you get the word like neuron coming into picture, and then the CA2, that is like an area where you will the particular area, CA2. And this you can also correlate with what the different sort of papers, the seminal papers that were published, that might have given rise to these terms coming up into these topics. Okay, so this was interesting that in science, in the same topic, how the different words keep on coming over time. Now this also gave rise to a nice application, that is, can you model what are the most influential articles in science, influential papers in science. So what will be the idea? Influential paper is the one that will affect the topic model, okay, that will affect the change in the topic model. So with each document you might have an influence variable, and the idea is that the change in topics are more affected by the influential papers than the non-influential papers, and that way you can model which article is more influential than another. So how will this model look like? So that is, influential articles reflect the future change in the language usage in that topic, and the influence of an article can be thought of as a latent variable, and what we will do, influential articles will affect the drift of the topics that they discuss. Okay, so that way we can model it as a variable, and the posterior that we will get for this variable will tell me how influential this article was. So again I make a very small change to the model, that is, now beta k2, instead of depending only on beta k1, also depends on this ID, okay, influence variable. So how influential this article was, again depending on the topic of this article. Okay, so now this ID is there with each document, and finally when I compute the posterior, I find out which documents get the highest influence. Okay, so whichever document will get the higher ID will be the influential article. So this will remain the same as the dynamic topic models, only now it is also estimated by this ID parameter. So each document you see here has an influential score ID, and each topic drifts in a way that is biased towards the documents that are having a high influence. Okay, this is a posterior that I will estimate from the data. and yeah, you can explain the changes in the future. Now, let us see another very interesting variant of LDA, that is, can we use it in a supervised setting? What do you mean by a supervised setting? So, till now we are saying I have a set of documents, in the document certain data occurs, and I give it to my model, and by using Gibbs sampling or variational inference, I can find out what are which different topics occur in different documents. That is what we can do, and we can model certain assumptions like how topics change over time and which are correlated, etc. What we are saying now in the supervised settings, can we also use it to do certain prediction? Like think about the movie reviews with certain ratings. So, can I use this model to say, okay, this review will get that many ratings. Suppose in the text, can I predict the ratings? Okay, or web page is paired with the number of likes. How many likes this web page will get? And the document paired with the link of other documents, or images paired with a category. So, lot of examples where the data points have some sort of class or a category. Can you also model it using topic models? So, you see there are two different ways in which it can be done. We will talk about supervised topic models and see what is the other variation. So, what is the idea? So, here, so you are modeling the documents along with the responses or the categories, and the responses are those they are fitted to find topics that are predicted of the response. That is, how do the topics tell about the response? So, how do the topics correlate with the responses? So, how is it done? So, you see this is the plate notation for the LDA model. So, this is what we had seen earlier. So, you have beta, k, alpha and all that. Now, what is additional here? So, you are drawing topic proportions and each word what is the topic assignment, plus for a given document, that is your data point. So, you are also finding out, so you are seeing what is the topic distributions for the document. From there you are sampling what is your response. So, from your ZDN you are sampling your response, that is like a normal distribution over eta transpose Z bar and a variance sigma square. So, what we are seeing, this response variable depends on the topic distributions with the variance. Okay. So, let us just quickly see what it means is that, so YT is sampled from a normal distribution over eta transpose Z bar and sigma square. Now, what is Z bar? Z bar are the topic proportions of this document. So, I know, okay, this topic T1 occurs 0.1 times, T2 occurs 0.3 times and so on. Eta are like the weights given to different topics. So, higher weight will be like if this topic is correlated with the higher response, and it can be negative also. If there is a negative response, eta can be negative. So, these are like the weights given to different topics. So, whether this topic will go to a higher response or lower response. And sigma square is, this will give you the mean, and then you will sample the actual response with this mean and certain variation. So, this will give you a scalar, right? Eta transpose Z prime will give you a scalar, eta 1 Z1 plus eta 2 Z2 and so on. This will be a scalar. So, this will be your mean, and with this variance you will sample your response. Okay. So, what you need to do? You need to find out what are your Z prime, and you need to estimate what are your etas. So, you have to estimate both Z prime and eta from your model. So, now we were saying there is also an alternative to using this supervised LDA. So, you can say, okay, why are we taking this complicated model where we are having to estimate eta also in the model? Why can't we run our topic model, get my theta for each document, theta d? Okay, that will again be a distribution over topics, and then run something like a regression. So, how does this theta gives me certain score, say liking of 5, another theta gives me -5 and so on. Okay, that is another possibility. So, I have different thetas for different documents, and I run a regression from this theta to my actual score, and this is called LDA plus regression model. And what we are doing right now is a supervised LDA, where we are sampling this inside my model during the estimation time. So, what will happen here? in this case you are not using the response as an observed variable, it remains unobserved in this case, whereas here response is also observed. So, what is the intuition is that if you take your response also as an observed variable, then your topics can be much more aligned to the actual responses, whereas here the responses are not aligned to the topics are not aligned to the actual responses, and you have to later find out a mapping from the topics to the actual responses. This can be done here in the model itself. That is why supervised LDA works better for predicting the responses than in LDA model plus regression. So, this is where you are taking the topic proportions theta and building a regression to find out y. Another model, so here response variable can be taken as an important observations to infer the topics in a supervised manner. So, that is the interesting thing here. So, what will happen? So, you will fit the supervised LDA parameters to document responses, and you will get the topics and the coefficients, so, right, and using these together, given a new document, you can estimate what is the response, eta transpose times expected value of z bar given the words in the document. This you can estimate from your SLDA model the same way you are doing from your LDA. So, what are the topic distributions for a new document, and this is what you get. Okay, this is from the Pang and Lee paper 2005. So, what they did, they took 10 topic SLDA model and fitted on movie reviews. So, you see here there are 10 topics, the most important words, and they are plotted with their etaj, corresponding etaj. So, a high eta means this topic corresponds to a high score or a high rating, and in negative value of eta means this is corresponding to a negative score, negative rating. So, what do you see here? On the higher side you have words like both, motion, simple, perfect, fascinating, power and complex. So, perfect and fascinating are nice words that are coming with on the higher side, and here you have least problem, unfortunately, supposed, was, flat, dull, and you can immediately see they are like a negative reviews. So, they are coming with a very low negative value, and this very nicely also puts your topics in a scale of minus to plus. That this was not available earlier. Earlier you had different topics, but you did not know whether this topic is for a positive or negative rating. Now you can also find out from your model itself, and it gives a very good held out correlation also. So, this is from number of topics. Even if you increase the number of topics, it gives a much better correlation than the LDA model. So, what did we see here? So, it enables model based regression where the predictor variable is a text document. So, you do not have to run the regression separately, that is run inside the model. Okay, inside the model itself you are sampling your response by using a regression model. Now, it can be used wherever LDA is used in an unsupervised fashion. So, you can use it with images, music, etc., wherever the data is paired with a some sort of response variable. So, you can also say that SLDA is some sort of supervised dimensional reduction technique, wherever LDA is a unsupervised technique, right. You are seeing the response, and by seeing that you are modeling your dimensionality reduction. So, that is about using supervised LDA. So, there are some other variants also for topic models. So, we will see some of those like the relational topic models and some simple intuition about the non-parametric Bayesian models in the next lecture.